I love this one. What if it's a big hoax and we create a better world for nothing? All right, what we'll discuss in this lecture is life cycle analysis, process chain analysis, input-output analysis, embedded energy, energy return on energy invested, and greenhouse gas accounting. And I may go a bit fast because, yes? Somebody say something?
No, that was just me going cough, excuse me.
I'm not sure why I thought this cartoon was appropriate. What does IDK mean? I don't know. Oh my God, no one knows. All right, so the objective of energy systems analysis is quite different than the economic analysis that you talked about. This is to understand the energy production and supply system and its relationship to consumer energy and the economy. So two considerations. One is money is not subject to physical constraints, but energy is subject to technological and resource constraints. So for the development of sustainable energy systems, it's essential to evaluate the potential of these to substitute for fossil fuels. So, the point we keep coming back to is, and sort of a central theme of this class, is that energy systems must deliver energy that is economical for consumer and profitable for investors. Neither one of these is sufficient by itself. They both have to be true. So this is a lovely diagram, a schematic conceptualization of an energy system, where we go from, here we enter the energy resources into the energy transformation system, say something like a natural gas plant, and then production and distribution. There's stuff that is waste heat, pollution, environmental impacts. We were talking about externalities. That's what in here. And then this contributes to the gross domestic product, goods and services, consumption, labor, and capital. It's like that. This is the system. So the flow of energy can be measured in any way we want to. And then the flow of capital for buying and selling can also be calculated in dollars or embedded energy or whatever. So here's a bunch of things that's in your book, table of explaining these things. We're not going to go into them here. And this is, then your book gets into the life cycle approach, which is inputs, outputs, and all of the things that go on. We're not talking about energy now. We're talking about using energy. So extracting raw materials, the energy needed for processing them, the energy needed for producing them, the energy needed to use them, and then the end of life. So this life cycle analysis is very useful for evaluating the economic costs of competing energy technologies or projects. And we could think about a parallel LCA, which would be the environmental LCA, where we would assess the impacts on the resource use, air, water quality, climate, human, and ecosystem health. So the ISO is an independent, it's called the International Organization for Standardization. So they try and standardize all kinds of things, and they've generated 25,000 international standards covering most of aspects of technology, has over 800 technical committees and subcommittees. So it has standards for conducting environmental life cycle assessments, analysis. So, this is an example of a life cycle assessment, with 4 steps: the goal, definition, and scope, the lifetime cycle of energy and material inputs and outputs, the assessment of impacts of 2, and interpretation of the whole thing. So here's life cycle analysis for greenhouse gas emissions for electricity generation. So this life cycle, greenhouse gas emissions, grams of CO2 equivalent per kilowatt hour. So biopower, photovoltaics, all of them, and then of course natural gas, oil, and coal. So we've talked about the fact that coal is generates so much more CO2 per kilowatt hour, and the fact that renewables contribute so much less, but nuclear does too, which is one of the interesting jokers in the deck of energy cards that we can consider. So here is the Green Design Institute at Carnegie Mellon provides free web-based economic input-output life cycle assessments. So I don't know if they did one for their lunch. Just giving you some examples of it. Now, this is an interesting thing. This is a little about the National Renewable Energy Laboratory, or used to be called NREL. Now it's operating as the National Laboratory of the Rockies, NLR, beginning in December 2025. And you can imagine who motivated the change in that name. And it's just here west of Denver in lovely Golden. So let's watch this. Oh, this one they took down. This is what is NREL, because it's not NREL anymore. And this one was also taken down. Now this one is NREL's 2023 top news story. So it'll give you a flavor of the sorts of things they do. Good start. I don't think it's done. Well, maybe it is. Okay. So part of what they did was this US life cycle inventory database. So you can, the USLCI database, US life cycle inventory database, provides individual gate to gate, cradle to gate, cradle to grave accounting of the energy and material flows into and out of the environment that are associated with producing a material, a component, or assembly in the United States. So this is related to process chain analysis, PCA. The PCA purpose is to account for energy and resources needed and waste produced at each step. And it's used in environmental life cycle analysis, embedded energy calculations, supply chain analysis, energy return on investment calculations, very wide range of activities. So basically, this is the process chain, right? The product stage to 0 to product stage 2. So M is material, U is utilities, S is services, E is equipment, and the outcome is joint projects and other outputs. So there's a number of stages in making anything. So here's an example that book gives of coal boiler fuel. So the coal in the ground to boiler fuel, you have to use trucks, diesel to get it out. You got to remove the overburden. You got to have acid mine damage that drainage you have to deal with. And you put it in a stockpile, and you have to crush it and dry it in the plant. And you have to transport it, right? And you generate P coal, which is the size that's suitable for burning in a coal generating power plant. You have to transport it. So that's the PCA for taking coal out of the ground and making it into boiler fuel. So here's an example. This would be a PCA analysis for making aluminum metal. So there's multiple steps. Each of them uses energy, and more energy is used in transporting. So here's a bauxite mine. Bauxite is the aluminum ore, and then it has to be transported to an aluminum plant to convert the ore into metal aluminum, or alumina, which is aluminum oxide. And then that is smelted. And then with that cast aluminum, you have to turn it into product, right? And we're all familiar with the product that we use, but this is in deciding to set up a new aluminum plant, you've got to do your PCA. So here is the steps in that. So there's the bauxite mine, the ore in the ground, and here's the outcome is a ton of sheet steel. So basically, these are all of the things that go into taking 4 tons of bauxite ore and making 1 ton of sheet aluminum. All of the energy inputs and all of the other inputs into here. And we don't need to go into that in any great detail, but I think it's pretty clear that the use of energy is critical in this whole process. All right, so that brings us to input-output analysis. And this is used by economists to characterize the effect of production in one sector of the economy on other sectors of the economy. And this is really quite interesting and quite confusing. Okay, so it was first developed in the old time, and then it was developed by this fellow in 1941. And it basically summarizes the interrelationships and dependencies between various industries. So we'll give a very interesting, simple hypothetical IO analysis. So basically, we've got a two-sector economy with coal and steel. So you need 3 tons of coal to make 1 ton of steel. And you need 0.2 tons of steel to make 1 ton of coal. So, use the steel to make tractors and things like that. Okay, so assume the demand for coal is 1,000 tons and for steel is 10 tons. So to do that, you need 210 tons of steel, requiring another 600 tons of coal, requiring another 120 tons of steel, requiring another 360 tons of coal, etc. So this is that table. And when you add it all up, it comes to something like, you need to do this, you need 2,200 tons of coal and 456 tons of steel in order to do this. Okay, and this has to be solved mathematically. Any questions about that? It's pretty confusing, but if you think about it, it makes sense. All right, so here we've got a very simple calculation your book goes through. So X1 is the amount of steel in tons needed to produce 1,000 tons of coal and 10 tons of steel. And this is X2 is the amount of coal in tons needed to produce 1,000 tons of coal and 10 tons of steel. So X2 minus 3X equals 1,000, X1 minus 0.2X2 equals 10. You have to rearrange, solve. And when you do that, you get these numbers. And you can use linear algebra, a matrix to solve more sophisticatedly. So this guy, Leontief, was won the Nobel Prize in Economics 1973, Russian immigrant, Harvard professor. And he's most famous for creating and defining input-output analysis. And it's fundamentally sort of influenced the evolution of economic analysis and accounts. All right, so you have IO tables that have been made for the US. And so you need to learn a little bit of nomenclature. So let's think about another two-sector economy, corn and biofuel. So if we produce $155 billion in corn, it includes $55 billion used in corn production, $70 billion in biofuel production, and $30 billion sold to consumers. And so the economy produces $205 billion of biofuel, including that. All this shown in the complete transaction statement. So here's the corn that you need, and the biofuel, there's the total. So you get total input, 155 tons of corn, 205 tons of biofuel, and it works like that. So this shows the requirement from each sector to generate $1 worth of output, and you basically divide the entries in there. So it's complicated. Don't worry about it. So with the total requirements matrix, then they can determine how production in each sector needs to change to meet additional demand. For example, if you assume that $30 billion more biofuel is required due to some new policy, and then you have to go through it, it's not, it's not as easy as you might think. You've got to go through all of these calculations, and you'll find out that new demand would require $18.5 billion more corn, 35 billion more dollars for biofuels for the entire supply chain in order to, make that additional demand. All right, then the book talks about embedded energy, which is calculated through process chain analysis or input-output analysis. It measures the energy cost of extracting, processing, and energy and the supply chain. And this is calculated for 1977, adjusted to 2008 using consumer price index of 3.51 due to inflation. And this is in your book. You can, if you have trouble sleeping at night, you can look at all these, but look at, they're covering everything, right? It's hard to imagine that it's only up to the M's, and this is all the way to the X-ray equipment. So find the three most energy intensive products. So let's see, energy intensity. There's 17,000, right? There's fifth, that's paving, primary aluminum, and synthetic rubber is what I see. Those are the most energy intensive industries. And over here, we're looking at cement. Cement is one of the major users of energy. Asphalt and lime, which is used in making cement. So those are your most energy intensive things in terms of dollar of product produced. All right. So your book goes through, let's do an energy return on investment example of something that we can understand pretty easily. So imagine 18th century farming. Here we've got a nice farm. We're collecting, looks like hay for the barn. And this was obviously the first energy system that was developed by people. We've got an input of S1 for food, animals and workers, and wood for heat, etc. And S2 is going to be our plows, harnesses, etc. for animals and things in the house for workers. And P is the produce taken to market. So a large ERI farm is one with a large EROI is going to be prosperous, well-fed, etc. And a low EROI farm will be poor and hungry. And a negative EROI farm will be no farm because it won't last very long. So anytime we're thinking about prosperity, we're really thinking about how do we get a strongly positive EROI. So here we go. Some more equations. Where the EROI is equal to the rate of energy production divided by the sum of energy input and the embedded energy used in production. Right? It's there's these two ways of energy involvement. So the only reason to build an energy production facility is if P is much greater than S1 plus S2. So in a way, it measures the energy profitability of an energy transformation system. So private industry is unlikely to invest in low EROI systems, but misguided government mandates, et cetera, can incentivize construction of low EROI power plants. Okay. Now, any project is the net energy N is all going to be less than zero at the beginning of the project because you're using energy to build the things. And the time when the cumulative N reaches zero is the energy payback period. So here we've got N over P, which is the the, let's see. Let's go back and make sure we understand what N over P is. So N over P, right? The net energy and the rate of energy production. So net energy or the energy production is, goes from 0 to 100% on this graph. This is the energy return on investment. So here we've got, oil in 1930, you got a lot of energy out for a very small amount of energy put in. So the EROI was almost 50, and the NPV was very high. Now, oil in 1970, wind energy, solar energy, oil in 1990, oil in 2010. This is the reality is that it's getting more expensive in terms of energy, which means dollars too, in order to find energy. Oil. And in contrast, the ethanol is at a very low energy N over P. The amount of energy that you get out is not that much more than you put into it. And this is why I spend very little time on biofuels. Is they're basically a political energy. They're not a good use of resources. So we think about energy. We've got hydroelectricity has the highest EROI, and the second highest is coal. Modern oil is getting EROI is getting lower and lower. Wind and solar have lifetime ERIs of between 2 and 60. If we think about oil from tar sands, the ERI is going to be very low, and we think about the heavy oil from Venezuela, it's also going to be very low. Ethanol from coal, similarly. All right, so this is the calculation of EROI, and the ERI supplements financial return on investment calculations. The financial return on investments requires assumptions about the future, right? The discount rate, the nominal discount rate, inflation. The energy return on investment does not, and they are complicated because of the embedded energy costs. So use the dollar cost, and then you can multiply it by energy intensity factors from this that table we just looked at. So here's an energy return of investment over the life of an energy producing project. So here's the energy output, the energy input, and the time period. So we've got the beginning and end of construction. It's going to be using energy, and then the operational lifetime. It's going to use some energy, but it's going to generate much more. And then the decommissioning will use energy too. So with this analysis, you can calculate the energy return on investment is energy output divided by energy input. It's going to be 25 over 5, so it's 5. And energy return differences between traditional, fossil fuels or nuclear generation and renewables are complicated in that traditional energy output is constant over time, day or year, location. Renewables are not. So these comparisons get more complicated. Okay, so energy return on investment and energy budgets. Energy budgeting is key for planning a sustainable energy future. Energy budgets include a lot of things. The energy required to maintain the energy infrastructure, the energy required to drill for oil, mine coal, obtain materials for photovoltaic cells and wind turbines, and the energy to find more resources. So your book shows this diagram and this diagram. So here we've got energy production. There's some heat rejected, and energy that's given embedded in the capital equipment. And then the energy that's available for consumption and for growth and production. That's related to that diagram we saw before. So here we've got a tale of two energy systems. So we've got the same amount of 100 units, at the beginning, and then coming into the energy transformation system, but relatively modest losses here compared to this one compared to this one, has much higher requirements for energy to build it and to maintain it. And then, so you can see that there's much more energy that is available for consumption and growth and production in this kind of a system than there is in this kind of a system, right? So this one has got an energy return of an investment of 25. This one is 2.5. So that energy budget has to be considered in all steps. So there is definitely a changing EROI of hydrocarbons. So the EROI is declined markedly over the last 70 years because companies have to drill deeper, have higher failure rate, and they find smaller fields. There are still oil fields to be found, but most of the big ones are offshore, and that's expensive too, in terms of money and energy. And obviously technology advances like horizontal drilling and fracking is helping a lot, but still. So as we said, the 1970 EROI was 25. Today it's 3 and 4. For oil sands, it's less than 5. For oil shale, it's about 2. And there are many more environmental problems with these than underground resources. So the energy return on a renewable energy has to be calculated, assuming some capacity factor, because these are not used all the time. So the book suggests that wind energy, with a 25-year lifetime, that return on energy is between 30 and 60, and solar and photovoltaics over 25 years with a 13% efficiency and a solar flux of 1,700 kilowatt hours per square meter. That would give you an energy return on investment of 5. Ethanol from corn gives you a negligible energy return on investment, whereas Brazilian sugarcane is much more, gives back a lot more energy per unit used, and something to think about. For renewables, EROI depends on the lifetime of the system, and it's important to engineer these renewable systems to maximize their lifetime. So here's an example of an energy return on investment for a wind energy system. This is a long time ago, 30 years, huh? Training, they have to build the tower, the labor, local equipment rental, lodging and food for employees, electrical grounding. The IO sectors are identified here, and the BTUs in 1970s per dollar shown there, and then the turbines. So the total is 1283 gigajoules for 2 turbines. So these are all of the things that had to go into it, foundation preparation, transformers, craning, labor. These are the costs, and the energy required in that. So this can be calculated, the total energy per installed 1.2 megawatt equivalents. Total energy input for the project is 3.89 times 10 to the 6 kilowatt hours. The total energy output is 65.2. You can calculate the energy return on investment. And today, our modern 8 wind turbine systems have much higher energy return on investment. And then your book goes into greenhouse gas accounting. And this is, something that is out there. So the Greenhouse Gas Protocol was first published in 2001, was revised in 2004. And it also looks at, the greenhouse gases and the upstream activities versus the and then the downstream activities. Let's see, watch this video.
This is a business, and these are greenhouse gases. Together, they have an amazing story to tell about profit, efficiency, resilience, and the climate. Like all businesses, this one wants to grow and be successful. It knows that being a successful business is about more than just selling products. That today's businesses track the health and profitability of their organization using a whole range of vital social and environmental indicators. And that greenhouse gases are one of the most revealing of all. Take carbon, for example. Managing carbon is a key ingredient to a successful business, and not just because it's good for the environment. It's also a way to save money, cut risks, and create exciting new business opportunities. That's why the World Resources Institute and World Business Council for Sustainable Development created the Greenhouse Gas Protocol. We work with businesses to develop standards and tools that help companies measure, manage, report, and reduce their carbon emissions. Over the last decade, we've helped thousands of businesses account for the greenhouse gases impact of their own operations and be more profitable as a result. It's made a big difference, but there's more to do. You see, every organisation has an impact that goes far beyond its factory gates or office reception. Take a company that makes cars, for example. Its impacts reach right back to sourcing steel and aluminium, through manufacturing the cars, delivering them to showrooms, driving them, and even recycling them at the end of their lives. Everything the car company does, from buying, producing, and selling its products, is called the value chain. With our new corporate value chain standard, companies can now see the full impact of their activities and figure out where they can make the biggest difference. For the car company, it comes down to answering questions like, what materials should we use? And how can we improve fuel efficiency? So now it can make informed decisions about how best to save money, design products, and cut risks in their business. But understanding the impacts in the life cycles of individual products gives businesses even more focus. Imagine the car company makes an SUV and also an electric car. Our product standard allows the company to work out how their impacts differ and how best to reduce emissions across the life cycle of each car, which means they can focus efforts on things like making the SUV more fuel efficient or working out the cleanest way to build and dispose of the battery for the electric car. Working together, our new standards give every business the ability to make decisions that increase competitive advantage, drive efficiency and innovation, and cut risks. If we apply them to thousands of businesses and millions of products all over the world, the positive impact on business and on the climate will be enormous. The Greenhouse Gas Protocol, the foundation for sustainable climate strategies.
Okay. So the Greenhouse Gas Protocol requires reporting of 7 greenhouse gases. Now, I don't think this applies in the United States. It may apply in Europe and some other places, but the ideas are still useful for us to think about. So these are the gases that people are concerned about. Obviously CO2, but also methane, nitrous oxide, hydrofluorocarbons, perfluorocarbons, sulfur hexafluoride, and nitrogen fluoride. These have different global warming potentials, and there are 3 scopes of reporting. So there's the scope 1 is direct greenhouse gases from sources owned or controlled by the company, factories, cars, stuff like that. The second one are indirect emissions from generation of purchased electricity used in company activities. And then other indirect emissions that occur as a consequence of company activities. And in Europe, I think in some countries, the first and the second are required and the third is optional. So these are the global warming potential values relative to CO2. So CO2, let's see, it's not in here, but these are lifetime of gases in the atmosphere. Methane is 12 years, hydrofluorocarbons, fluorocarbons, nitrous oxide, sulfur, fluoride, nitrogen fluoride. So this is the global warming potential for each of these per unit.